Welcome back to the online seminar series, Machine Learning Needs Mathematical Optimization. Today is the last seminar of our third season. And this seminar will be presented by Marc Sevaux, the president of. Before we go, this a brief introduction of the speaker, I would like to remind you that we are to come back after the summer with season 4, and you have some of the speakers over here, and we thank you for coming back Monday, and we So, Marc, thank you very much for agreeing today to introduce our speaker, and the floor is yours.
Okay, thank you. I hope everybody can understand me correctly.
Yes, we can.
Yes.
Okay, so Dr. Radhika Kulkarni, I was asked by the organizer to make your introduction, and as always, it's not an easy task, but it's always an honor and a pleasure. Radhika, if I may call you by your first name, we had not the chance to meet in person before, and I regret it, especially when I dug into your profile while preparing this introduction. You hold a PhD in operational research from Cornell University since 1981. You work in the area of operational research, artificial intelligence, machine learning, statistics, econometrics, forecasting, data mining, and many more. And you have been recognized as a key contributor to scalability and performance of algorithms in all these domains. You have a very impressive professional life, former Vice President of Advanced Analytic Research and Development at SAS Institute Incorporation, responsible for the world's leading analytics software products portfolio, creation of the AIOR AI ML Center of Excellence, served on many academic advisory boards, including North Carolina State University and Georgia Tech, member of the Advisory Council of the School of Operational Research and Information Engineering at Cornell University. You have been recognized as an Informed Fellows in 2014. You have been the winner of the award Women in ORMS, and now you are the president of Informs. Where are you going to stop? You know, after this position, you can still be president of IFORS. I was also struck to read that since you retired, you seem more active than ever, especially with your actions for motivating students to pursue their studies, inspire interdisciplinary collaboration, or your insistent work to link industries and research. As president of Informs, you have to face quite a number of challenges, and I'm sure that you will sort this out as you have solved many problems in your life. I'm happy that Informs, the Sisters Association of Euro, has elected you as president, and I can tell you today that I vote for you. But today, you are not invited for Informs. You are among us because you have been recognized as a specialist of OR, artificial intelligence, machine learning, data science, or for the links you have created between these domains. Today you are the invited speaker of this seminar series called Machine Learning Needs Mathematical Optimization. And today we can say that machine learning needs mathematical optimization needs you, Radhika. So the floor is yours.
Oh, wow, thank you so much, Marc. If my husband were to hear you say that I have a next job as president of IFORS, he's going to run away. Thank you very much for your lovely introduction, and you're very kind. And thanks, Dolores, for inviting me. And I'm very, very happy to be here to share my experiences. And I know this is the last of the series, this particular session of the talks. And all the talks so far have presented many research opportunities where you can see that machine learning definitely needs optimization. I will give a perspective from what I have seen in industry over my career of about 35 years at SAS, and now volunteering for many other roles. So my talk will be less technical, but more about the applications. So I hope I can share some of my insights, which will be valuable to all of you. So my themes will be, what are the critical business problems that drove me to do whatever I did when I was at SAS and my team, and what were the opportunities for innovation that I saw and my team worked really hard on that. And all of them, I believe, succeeded because of lots of interdisciplinary and multidisciplinary methods. And I'm a big, passionate advocate of all of that. And I hope I can share my passion with you. And analytical innovation is great. You need to have that. But is that enough? So I'll talk about some of the barriers to implementation and how you can succeed despite that. All of us have heard about the world of big data. Maybe it was 2000, early 2000, 2010 when everybody started talking about big data. And now data comes out of every possible application, your cars, your appliances at home, Twitter, Facebook, all kinds of ways in which you get data from everywhere. And the question is, do the data give you any value? Can you get some value from them? And how can you look at the different sources of data? And something I recognized very early on in while I was at SAS, where I was heading up the advanced analytics R&D, we had many different groups. Each group worked on different specific research applications, data mining, optimization, forecasting, and so on. And each one of these teams looked at data in a different way. The types of data they analyzed is different. So for instance, if you're looking at predictive modeling and you're trying to figure out who will respond best to a particular campaign, you have data which are like rows of numbers, and each row represents different demographic or other variables about a particular person. And you look at that, you analyze it, and you figure out what is the best chance of getting some offer accepted, who should I send it to. If you're looking at forecasting, you have time valued data so that you can look at the trend and say, what will the sales look like in the next month, in the next season? What will the sales look like in North Carolina? What will it look like in Copenhagen? What will it look like in different parts of the world? So those are all different types of data. And for each type of data source that you get, you require a different and specific modeling technique depending on the business problem that you have. And in addition to all these numeric data, what made life even more complicated was data started arriving in forms of audio files, in terms of video files. And that's where the explosion of data happens. And then you need even more innovation and innovative techniques to be able to get value from them. So what I will talk about is what are the different ways in which you can use analytics, all these different flavors of analytics, to take data that you have and get value from them, and where are the opportunities for insight and innovation. So each domain group, each group looks at data and they're used to one particular kind of data source. So again, I'll go back to the predictive modeling techniques where you're looking at demographic data and looking at individual characteristics of the people that you're studying. So what we realized is that if you augment your legacy data source with some auxiliary data, you can actually get a lot more insight. And I'll pick a couple of examples which show how you can do. So if you had these demographic information about individuals and you're trying to make an offer for a credit card, let's say, or a cell phone, new iPhone, etc., then now, instead of just looking at people individually, if you also look at some of the network data, you get a lot more value. And I have a few examples where we've seen that happen. In addition to that, something that I recognized and I instilled in my team, the recognition that if you're working in individual teams, depending on your domain expertise, you can do something. But if you interact and work with others, for instance, I come from an operations research background, so I always felt that optimization can be very valuable in multiple domains. And so that interdisciplinary collaboration is a very valuable thing. So it's not just machine learning that needs optimization, but statistics, forecasting, you name it. All of these techniques can get a lot of value from optimization and operations research techniques. And those are some of the examples that I'd like to talk about. In addition to that, if you're trying to solve a business problem, it's not just individual domain analytics that helps you, but you need to combine multiple approaches. And so I'll give some examples of those as well. So the network data that I mentioned, you can exploit network information, for instance, in fraud detection. So if you know, for instance, that you're analyzing some fraud for healthcare fraud, and you see that there is a particular practice of physicians where there have been some fraudulent claims, then you look at all the physicians or the patients that are associated with that node, and you can start exploring, and there's a better chance that you might find some more fraudulent activity like that. So that's what I mean by saying looking not just at the physicians individually, but looking at the networks that they're connected to. Likewise, terrorist network detection is again the same kind of thing. Targeted marketing, which I mentioned again. So if I have 100 Facebook friends, but somebody else has 1,000 Facebook friends, I guess the credit company or the telephone, the new iPhone is better marketed to somebody who has 1,000 friends, because he's likely to talk about it and get more. The company gets more sales out of it. So these are some of the applications where I think network information added and augmented with the typical data set that you look at gives a lot more value. And everybody has seen all the effects of contact tracing and how you can contain the spread of the virus in this COVID world. And we've seen a lot of value in just seeing who is connected to whom. So exploiting auxiliary data gives you a lot more insight, and there's scope for innovation there. So in my early days, as I was leading this team of multidisciplinary researchers, something that we recognized is in statistics, data mining, machine learning, in each one of these, there were lots of value or lots of opportunities for using optimization techniques. And I've got a few listed here. And for support vector machines, we've realized that it's you can use a large quadratic optimization technique to solve that. And many times, some of the innovations that we saw in the interior point methods and the ability to handle larger and larger problems helped us solve these problems in support vector machine modeling very well. Quantile regression, this was a technique that many of the statisticians on my team had studied in graduate school, but it was always left aside as, okay, this is not really that important because you don't really have that much data at the ends of the spectrum. But as larger and larger data sets grew, the quantile regression became a technique that was quite valuable. And again, it leads to large linear optimization problems within the modeling technique. Deep learning, we all know many of the deep learning techniques use stochastic gradient descent methods, etc. And reinforcement learning, if you couch it in terms of operations research terminology, we think of it as partially observable Markov decision processes. So likewise, one of the very interesting problems that my team worked on was in optimal binning in credit scoring. So credit scoring, they do a lot of work in trying to figure out how to bin the respondents, how to bin the applicants, how to bin the customers into different buckets so that they can rank them in terms of better scores, etc., etc. But then they have lots of constraints that they need to impose on them. So anytime you have a modeling problem like this, where you have to impose constraints, where you say that a 65-year-old, if the same other demographic constraints or values are pertaining to a 65-year-old, whereas compared to a 50-year-old, the way that these decisions should be made, there should be some monotonicity. You can't just suddenly change things. So once you start putting those kinds of constraints and say they need to be at least 5 bins here or maximum of 10 bins, you enter constrained optimization. So again, we used some mixed integer nonlinear optimization techniques to solve that. And something that was very interesting is that when you're trying to do observational data studies in statistics, where you're not really doing a clinical trial, but you're looking at observations from already drugs that have been deployed and have been given to patients, you want to still go back and do an analysis on whether the drug really made a difference or not. So you have to go back and look at the people who got the drug and those who have not, and try to do a matching of the people on other various demographic variables, so that it's almost like you had done a clinical trial, but now you're looking at it post facto. So we call that propensity score matching. So we realized that we could use some graph algorithms to do that. So these are all the ways in which we found that the operations research tools that we were developing in-house could actually be used to augment some of these other analytical processes and modeling. So, so the other area I mentioned for innovation is when you can combine multiple techniques together. So when you solve a business problem, like in retail, for instance, if you're doing a regular price optimization or markdown optimization, you need to do forecasting first. Well, you first need to have data, then you need to do some forecasting, and then do some customized algorithms for the problem of clearance optimization or markdown optimization or regular price optimization. And in all of those cases, you're requiring all these people to come together so that they bring their problem and they're able to discuss and say, okay, your standard tool for your mixed integer nonlinear optimization or whatever is not really going to work for us. We actually have a stochastic problem, and it's like a dynamic programming, but it's hard to get a dynamic programming algorithm that works in general. But if you put the specific business problem in the context of what you're trying to solve, you can get a custom algorithm. So this is where getting people from different domains to sit down and talk at the same table and discuss the problems is where we found that the whole is greater than just the sum of its parts. So these are some of the various ways in which both interdisciplinary collaboration and multidisciplinary collaboration gives huge benefits. So while we were doing all of this, maybe 15 years ago, the data volumes continued to grow along with the problem complexity. So the volumes of data were increasing in leaps and bounds, and the capacity of the compute power also kept increasing in leaps and bounds. And so the business need was growing too, where now that you have the ability to solve all these large problems using large data sets, then can you actually get better prediction if you do microsegmentation? So instead of looking at the problem across the whole country or the whole nation, can you look at it county-wide or statewide and look at different prediction problems, forecasting problems? So microsegmentation for making offers, for treatments, for forecasting sales, etc. All of these became very important. Along with that, you also had this situation where if you have thousands and thousands of models now that you're trying to compare and pick the best model, automation became very, very important. So you want to be able to pick the best model automatically. Anyone who's done predictive modeling in any of these competitions that you see, the Netflix prize and all these different competitions, Kaggle and all of those, you'll find that the winner is usually somebody who's been able to spend a lot of time looking at lots of models with lots of parameters. Now, if you can get a machine to do some of these automation very fast and compare them, then you're doing a good job. So you can get a better model. So not only are you looking at multiple types of models, neural networks, decision trees, gradient boosting methods, etc., but then each type of analysis, you want to be able to pick the best parameter that fits the model best. So automation across thousands of models became very, very important. So decreasing latency is one of the goals that everybody is trying to achieve. So with that in mind, some of the types of problems that we could tackle became very, very interesting. So I think of this as a golden era for AI, machine learning, and data science, because you can make better business decisions more rapidly in a very, very connected world. So you have data, which are growing in leaps and bounds, computing power, which is really surpassing everything we could have imagined possible. And then there are lots of researchers working on innovative algorithms to solve different kinds of problems. So it became the new frontier for us in scale, speed, predictive modeling, and being able to do data-driven decisions more automatically. So some of the types of problems we encountered were in the automation, where auto-tuning became very important. How do you automatically tune the hyperparameters of a model? When you have micro-segmentation, you're not only looking at the models for every single thing, but all of them together, all these different sections, all these different segments. And feature engineering is a term that's used very much in computer science. It's not so much used in optimization or even in predictive modeling, where what they mean is just wherever you do transformation of variables. We all know that when you're doing a statistical analysis, sometimes you transform the variable to get to be able to do a better model fitting. So those are all where you're transforming variables, combining variables. The term feature engineering just refers to that. So in all of these, now you say, okay, what if I did change these variables to these transformations, or I combine these variables in these fashions? So how in every one of those, the number of models that you have to build and the number of models that you have to analyze explodes. So automation becomes very important. And that was a place, again, where some of the local search optimization techniques that my team was building became very, very valuable. Some of the genetic algorithms and some of the other local search optimizations that we, derivative-free optimization techniques became important in model selection. So for the intelligent search in parameter space, to find the best model across different modeling applications, and sometimes incorporating business rules into the model selection, etc., etc. So those were all areas where some of the local search optimization got a resurgence in my team. So we said, hey, these are places where you can use them very effectively. So the opportunities of analytical innovation kept growing as we looked at these different types of problems. In addition to that, as we hear the term Internet of Things, where so many different machines and various different artifacts are connected to each other, the interconnected world, data is coming from all sides. So we have different kinds of data where the data frequency grows in leaps and bounds. You also have streaming data. So the types of methods and techniques that we needed to solve these problems had to change as well. We needed innovation in those areas as well. So some of the here's an example where for surveillance video, when you're trying to detect nefarious activity, for instance, if you look at this, the original video has actually all these, oh, sorry, let me go back here. The original video has everything together, the people in the screen, the stationary objects, etc. What we really needed to do was to separate the background from the foreground. So the background is all the stationary objects, and the foreground are the people that are moving around. So we ended up having to augment or modify or innovate with the principal component analysis to separate the effects. And we developed some techniques which we call robust principal component analysis to do this. And so this enables you to look through the video and separate the foreground and background and be able to decide which ones are really, so if you look at the background and you see that something has suddenly appeared in the background which is not moving because maybe someone has left their backpack, and started moving away, that's where you hear, hey, someone has left their backpack and maybe there is some problem. Is there a bomb in there? Is there some problem with that location, etc.? So detecting nefarious activity is one of the applications where we looked at. Monitoring beehive health. This is an interesting area as well, where again, looking at streaming data, and the beehives are, you need to look at the health of the bees, the health of the beehives, and see what is happening to the queen bee. Is the climate in the beehive really stable? Is there some problem? Is there some stress happening so that the queen is forced to leave the beehive, in which case the beehive perishes? So how do you make sure that you are monitoring the beehives without having to actually go every day and look at it, or every half an hour, few minutes, etc.? So we collect the weight of the hive, the temperature inside, the humidity, etc., all these parameters, look at it and detect. Again, it was again using the principal component analysis, where we looked at ways in which we can detect if there is some problem happening. So in manufacturing, detecting defects automatically, here is streaming data. So you need to look at streaming data. And when you're looking at very, very expensive chips being manufactured, microchips, then the moment a defect occurs, and if you don't catch it right away, there could be thousands of wafers which go by, and that is a huge loss. So you want to make sure that the moment a defect is showing up, you catch it right away. So these are like hugely scaled up version of quality control techniques, where you're looking at information that's coming from many, many sensors. So it's not just a univariate value that you're looking at multiple variables, and and you need to make decisions very, very quickly. So we call that an analysis of streaming data. And again, you need to invent some new techniques, and automation is very, very valuable. So the Internet of Data in transportation, this is an application that we worked on with GE Transportation, where the problem is that these locomotives travel across thousands of miles, and they could be, if a problem happens and there's a train derailment, and if the train is carrying some hazardous material, it could cause a huge problem. So there are lots of regulations on what is called positive train control. So what needs to happen is, if there is a problem in any of the sensors, there needs to be a decision made right away that we need to stop the train. So there is not enough time for the data to go to the control station and for the decision to be made there. It has to be made right away. So we call that edge analytics, where the sensors on the train monitor, and the decision, if there is a problem, has to be taken right there. And so these are some of the ways in which the analytics ecosystem evolves. So the at-rest analytics is what we think about traditionally, where you have gathered a lot of data, you're doing analysis, predictive modeling, forecasting, data mining, etc. And that's data that is at rest. There's also in-motion analytics, where you're looking at fraudulent credit card transactions, or the defects in the wafer manufacturing. So as the data are moving through the system, you want to make decisions. Or edge analytics, where some machines have been deployed in a faraway location and you're not there to monitor it day in and day out, or frequently enough, and then you need some decisions taken right there. So these are all the types of problems that we worked on, where a huge amount of innovation needs to happen. And again, getting the database workers, the database people who know more about database architecture, etc., and the predictive modeling, optimization, machine learning, and all of these forecasting folks to work together, we kept innovating in all these areas. So the entire analytics life cycle actually starts from the data, the discovery, and deployment. Something that we never remember is what you have found out, is the problem that you have solved, is the solution that you have prescribed, is that really deployable? And once it is deployed, is it really maintainable? Is it sustainable? Is it have the data changed? Do you need to look at it again? And so these are all the different ways in which you need to maintain this analytics life cycle. And for people in practice, in industry, that is very, very important. So when we go and consult with companies, it's not just the problem solution that we've come up with, whether it's actually deployable. And that's where I move on to the next phase, where I want to talk a little bit about analytics innovation, and is that enough? What do I believe are the critical barriers to success? Whether you have the right data or not, whether you have the right process, and whether it is acceptable, and whether you have the right talent. So these are all key ingredients for the success of any analytics project. So do you have the right data? And this, for all of you who've done a lot of work in machine learning and optimization, it is probably something that you're very, very well aware of. But I've put a link in the slide for a wonderful TED talk by Joy, by a researcher called Joy at MIT, who found that the facial recognition data was not recognizing her. And we've heard these types of examples quite a bit, where the training data missed a huge demographic. And so the actual models were not able to recognize some certain types of people, certain demographics of people, and so on. So making sure that you have the right data taken from the right source and put it all together, that's very important. Another, this was an experience that was very interesting for me. Do we have the right executive support for changes that you need to make to implement? So I'll talk a little bit about this particular problem. It is a typical offer optimization problem, where a bank or a credit card company or a mortgage lender, they have thousands of customers, and they have new offers that they want to make. So the new offers could be a new credit card rate offer, it could be a new mortgage offer, etc. So there are multiple offers, and they can make these offers through multiple channels. They can either call the person, they can send them an email, they can send them a regular mail, etc. And the products that they're offering could vary from checking accounts to mortgage to savings accounts and so on. So now, and you have a certain fixed budget. You can't make all these offers to everybody in your customer base. So this could be where you're trying to acquire new customers, or you're trying to cross-sell to existing customers. So you can imagine the problem actually is a very, very large mixed integer programming problem, because what you're trying to do is decide which of the customers do you make an offer to, using which channel and what product. And so it's with thousands and thousands of variables, and it's a 0-1, whether you offer this person this choice or not, etc. So this is a huge problem, and we were very, very thrilled that we got a really nice way to solve it very efficiently, etc. When we went to actually implement it and talk to some of the customers, the challenge we found was not because they didn't trust us that we had a good solution, but they said, how are we going to sell this to our campaign managers? So if you look at a particular campaign, and if you've got 100 different campaign managers, and each one of them, in the previous way they handled in the business as usual, each one of them would be given a certain budget and a certain number of offers they could give, so they could manage their own. But now you're saying, we have the ability to solve this as a mega optimization problem. So we can put all of these together and put them all together, and you have millions of constraints, millions of whatever. And now you can figure out, maybe you give more offers to this campaign manager, none to this campaign manager for this particular season, and so on. So now, how do you explain that? How do you tell the campaign manager who's not getting the offers that he had originally got, that you don't have a campaign to run in this particular month? How do you say that? How do you sell that issue? So this is where the executive in charge needs to understand that what you're doing is a global optimization problem, in which case some of the local people may not think that they've got a good solution. So do you offer them different incentives? So here is where some of the executive support for implementing these solutions became very, very important. So we had to learn how to talk about it, how to talk to the executives and figure out, okay, if this is what we are trying to propose to you, but you need these types of changes. These are the types of changes you need to implement in your processes. So the process that you follow for actually getting a successful application deployment becomes very important. Do you have acceptable results? This is a topic that is very much a topic of research these days, because more and more you hear whether the solutions that you're providing or you're proposing, are they interpretable? And I think Professor Cynthia Rudin was one of the speakers in one of the earlier sessions I saw, and she does a lot of work in this, whether the predictive modeling techniques are interpretable, explainable, is a black box explainable? Is it the same as an interpretable machine learning, etc.? So you can look at it from different perspectives. From a data scientist or the modeler, he's trying to look at different ways in which he's improving the model, whether it's the appropriate model or not. So being able to understand the model is very, very important. You might wonder why, despite all these many fancy techniques, decision trees are still a very, very valuable predictive modeling technique that gets used a lot, because it's easy to explain that if this and this and this happens, you make this decision. If this happens, you don't take that decision, etc. Whereas a neural network or a gradient boosting method may be harder to explain. So the data science modelers, the consumers, you want to be able to explain to him or her why somebody that seemed ostensibly to have the same type of demographics was able to get a loan, whereas I was not able to. So how do you explain the results? Are they being treated fairly? And more attention is coming up where you're paying attention. The authorities, the regulators, the policymakers are looking to make sure that the decisions that are being proposed, are they fair? Are they transparent? Are they acceptable? So this has become a very, very important area of research among the researchers working in machine learning. And many a time, some of these interpretability types of issues that come up, explainability types of issues that come up, impose constraints on your machine learning models. And I think that's where it becomes very, very valuable to say you can use some optimization methods, whether it be integer programming or nonlinear programming, to be able to impose those constraints and be able to satisfy some of the constraints that are required for making the decisions better acceptable. So ethics and AI is an area where a lot of research is going on and where there is a lot of attention being paid at the highest levels. Does the solution deliver fair and equitable outcomes? Does the solution introduce or exacerbate bias? And so all these different questions come up, and you need to be able to answer them in an equitable way. So these are some of the ideas for research that are very, very relevant in today's date. And the European Union has since, I think it was in 2019, if I'm not mistaken, there were specific ethics guidelines for trustworthy AI that were put out and published. And so the three broad principles are they lawful? Are they ethical? Are they robust from a technical perspective, and taking into account the social environment? So again, I've got a couple of links here where there is more detail about the types of questions they're trying to answer with these techniques and methods. So the other question that people talk about a lot is, do we need to have humans in the loop, or can everything be automated? I talked about automation quite a bit, But the question I ask is, would you get on a plane without a real pilot? That the plane flies with mostly an autopilot is driving the plane and all of that. But would you go on a plane if you know that there is no pilot in the cockpit? There are lots of questions that are coming up with driverless cars. When will you get to the stage where you can say, I can safely sit in a driverless car and feel comfortable about it? This particular example is a really good example where one of the AI journalists had a nice example of the Viking Sky cruise ship incident, where I don't know if you're aware of that, where this cruise ship was stuck in stormy waters and it was jostling a lot. And I believe it was moving so much up and down that the fuel level would fall below the safety that was needed, right? And so the automated sensor detected that it went down and said, oops, there's not enough fuel. So it decided to shut down. So the question is, in that stormy weather, is that the right decision? Would a human being, if he had been paying attention, would he have said, oh, it's because of this jostling, if we stop the ship and we are not able to anchor in a safe place, it could actually lead to bigger trouble. So it's a very interesting article, and you can see the arguments that are made as to why it is important to have humans in the loop. So I believe that human AI plus humans will lead to better results. So at least right now, you do need humans to recommend the strategy based on AI insights. So I talked about some of the problems that we solved and the types of research that we were working on. So now in my current role as on the Informs board, we've been spending a fair amount of time in saying, where can operations research as a discipline have more relevance in the world of AI? What are the things that we need to do so that the CS or computer science community, the machine learning community, is aware of the value that OR can bring? And likewise, what are the types of problems that arise in machine learning and all the typical AI problems where optimization researchers can play a big role? So we're not trying to say that one is better than the other or supersedes another. It's that being able to discuss and solve these problems gives you a better chance at success. So last year in 2021, we had an AIOR workshop, which was conducted virtually. It was conducted between Inform CCC, the Computing Communities Consortium, and the ACM SIG AI. And the goal was to bring the OR and AI communities together and articulate some research and education opportunities for each discipline. Often we found that the language that we use for the same type of problem is just different. So when you come down and say, okay, what problem is it you're solving and how are you solving it? Some of the techniques are not that different. It's just that we look at it from different lenses. So this was the goal of this first workshop. We plan to have 2 more workshops. There'll be another one in person later this year in Atlanta. So and I've put a link to this workshop, which also has a link to some of the presentations, most of the presentations that were presented there, and all the discussions that we had. So I think these are some of the ways in which I'm still continuing my journey and trying to figure out, okay, where are the places where OR can be relevant, optimization can play a bigger role, and be better recognized for the value it brings. So these are some of the endeavors that I'm doing. The final question I have is, do we have the right people? And this is where many of you who are in education will see the value, the problems that I described, the type of problems that we are trying to solve. It's not just the sole discipline, analytical discipline, and its research that is important. It's the data, it's the ability to see beyond what is required, the adaptability, the acceptability, the deployability. All of these become important. So you need to be prepared to train the folks who are all needed for making an analytics project successful. They need to be the leaders of the group. They may not be experts in any discipline for that matter, but they need to understand enough. So their training is a little different. People who are building the algorithms and the methods, their training is a deep PhD in those research topics. Then there are people who look at models that are existing and be able to interpret them. Nowadays, more and more software companies are building automated tools. So you don't really need to build the nitty-gritty detail of the algorithm, but you need to understand what the algorithm is doing. So exploiting analytical tools, creating models that can be applied, and database engineers. So all of these are important for the success of a project. And I believe that it's an important to recognize that all of these are important, and many schools in the US now are looking at undergraduate education and associate degree type of thing, where you can train people to look at not necessarily the research problems, but how do we use research, or how do you use the models, how do we translate the model and use the tools that are at hand. So increasing analytics literacy at all levels is a very valuable goal. And again, I put a link in here, which is a nice discussion. It's a booklet, actually, talks about building successful OR and analytics teams. And I think that's a great link, which I found very fascinating. So I think with that, I'm coming to the last, which basically says, at the end of the day, to succeed with analytics, you need to learn to work with new sources of data, new types of data, new analytical infrastructure. How do you exploit it? And of course, you'll always need new algorithms specifically for customized problems, and educate and train your workforce. So with that, I thank you. Thanks. And I'm open for questions.
Radhika, thank you so much for this amazing presentation that gives us a lot of ideas. For the audience, remember the way we do it normally. So please raise your hand, and Jasone will give you rights to the microphone and the camera. And Mark is running the Q&A session.
Okay, I will do my best. Thank you. Thank you for this presentation, Radhika. It was really great. I'm not sure how I can see the raised hands, but I see that there are 9 hands raised.
I can point that out. Yeah.
Okay, please.
So remember, if you have a question, just raise the hand, and yeah, we will give you the rights.
Okay. Anyway, I have a question for you, Radhika. And
Okay.
when you talk about human in the loop, and I was interested to know or to understand what might happen if a human in the loop is too confident by his AI system, and he can be blind by the fact that it trusts too much the system. So how can let's say a company or a group or team can manage this too confident human in the loop?
That's a very, very important question. And I think this is where the leadership comes in, right? You need to make sure that your analytical leaders do recognize the fact that there is such a thing as overconfidence, right? And it's the problem that we've always had in other types of places, where you hire some really, really smart, brilliant people who think that they know best, right?
Yeah.
And if they think that, okay, this is working perfectly, you have to make sure that, I always say that having enough examples to say, okay, look at it this way, what do you think would happen, right? And always another leadership quality that I admire in people is the ability to see the big picture. So the leader always, and in fact all members of the team, need to be able to understand the big picture and look at it from all perspectives. So you need to be trained to say that, okay, this is what you're saying, you're thinking this way, but always question it, right? Why? Why do you think so? Have you tried some simulation? So simulation is something that people do use quite a bit. And again, this is a place where operations research training gives you the ability, the base tools to do some simulations. So do the simulation to make sure that, okay, this is not something, so, that could go wrong. So be able and be willing to speak up. So, and encourage people in a team to speak up. So somebody will point out, hey, that's not right. So if there's someone there, encourage him.
Yeah, I agree. Okay, I don't know if we have questions. No more questions. Nobody. Dolores, can you help me if there are some?
Yes, I can. No, at the moment there are no more questions, but I do have one. Well, yes, I have here Juicy Rusk. So, Jasone, can you give the rights to Juicy?
Yeah, I've given them.
Thank you. Juicy, you can unmute.
Can you hear me?
Yes, I can hear you, Lucy. I can hear you.
Okay. Sorry about the confusion. Had some
No
technical
problem.
problems. Thank you for the interesting talk, and I think it brought out many interesting points mirrored also by my experience in similar topics. My question is, how do you see you mentioned the automated parameter tuning and automated algorithm selection, but how about this automated feature engineering that is kind of coming from the deep learning side? That it's kind of the learning algorithm itself learns the best way to do the feature engineering. Do you see what will be the end game of this? Will us be needed anymore in anything basically?
So that's a good question, and I do think I think that's one of the values that these really sophisticated deep learning algorithms bring to the table, right? Because they're able to learn from the models that they're building already and automatically modifying it and changing all of that, right? And I think it's just brilliant. It's almost like magic, right? How these algorithms work. And I do think that there is huge value in all of them, but always look at it and make sure that they mean. And I think this is where the interpretability and being able to just to understand what is going on and doing some business as usual versus some comparisons against business as usual is very, very valuable. And looking at some holdout data and what is it doing with the holdout data and looking at all of that. So those techniques which we've used in the past are still valuable here, right? Comparing to business as usual, looking at how the model is interpreting different types of data, etc.
Yeah, thank you. And it's true that the deep neural networks are kind of black boxes, and that is the advantage of the more traditional models. Yeah. Thank you.
Yeah. Thanks, Juicy. Thank you.
I don't know if we have more questions. I cannot see other hands. Yes, there is one hand raised by Anurag. You are not presented, so you can speak.
Hi, Anurag. Can you hear me?
Yeah, sorry, I was on mute. Thanks, Radhika, for your time today. It was a great insights listening to all those topics there. I wanted to understand in terms of your point, like you were saying that that lots of applications we can kind of take over as an area and try to kind of optimize the problems and algorithms in machine learning, right? So one such area kind of I was thinking was that how can we kind of try to, if we take this machine learning algorithms like decision trees, and suppose if we have support vector machines or artificial neural network, how can we kind of use our operation research modeling techniques like stochastic programming or maybe mixed integer programming, and see this as a problem of mathematical optimization and try to
Yeah.
solve this machine learning algorithms. Maybe as an example, like using stochastic programming, can we kind of think of this as some uncertainties in the data or in the algorithm itself? Like what kind of approach we can take there?
So, good question, Anurag. Personally, I'm not too familiar with the stochastic programming techniques that have been applied. I do know that when you look at decision trees and all of those, there's a lot of work that's been done by Siemens in optimal decision trees and looking at various optimization techniques applied on top of those. And Cynthia Rudin is one of the great researchers also who's done many of these superimposing optimization on top of predictive modeling techniques, right? So other than that, I haven't really looked at it very closely. So
No,
I don't have any much advice to offer there. I'm sure somebody here might be able to give some insight as well.
no worries. Radhika. Thanks so much. Yeah, thanks, Mark.
Okay. Thank you for the answer. No more question. I cannot see no more questions. So last chance to everybody to ask a question. Otherwise, this is the end of the session. So Radhika, I would like to thank you once again for this excellent presentation. And thank you, Dolores. I give you the voice if you want to say a few words at the end also.
Thanks, Mark. Thanks.
Yeah, I would like to thank very much Radhika for coming today. You are on a very, very busy agenda, and making the time for this is highly appreciated. And for the rest of the audience, we will see you back after the summer with more talks. And thank you very much for the support that you give to this online seminar series. Bye-bye to everybody. Have a great summer.
Thanks, Dolores. Thanks, everyone, for attending.
Thanks, Dolores. Thanks so much.
Thank you so
Thank you,
much.
everybody.
Thank you.
It was a very nice talk, Radhika.
Thanks, Dolores. Thank you. You're kind.
Yeah, you get lots of people thanking you. So,
Oh, thank you.